Okay, in this video we're going to look at one of my favorite tests and one of the most important convergence tests there is, the ratio test. First of all, I would like you to go and answer these three questions on Schoology. This is the quiz for this video. Just to say if it converges or diverges, let me give you a couple quick hints. When we're looking at things like this that are polynomial on top and bottom, not a bad idea to think about using the limit comparison test. It would work pretty well. You know, what you'd compare to, I usually look at kind of the biggest stuff and say, well, what about like 3 over n squared? Okay. For the second one, it's really hard to compare things when it's not expanded. So maybe begin by expanding this, and then maybe start thinking limit comparison again. And if you need to look back at what it takes to converge, you sure can. And on this final question, you'll notice that we've got a integral going from 1 to infinity, so it's obviously improper with an infinite bound. So, maybe set it up that you're going to have the limit as b goes to infinity, right, from 1 to b. Okay. Now, what I would look at with this would be, because it's a fraction, I wouldn't use integration by parts, not really factorable, so I would maybe look to use substitution. Maybe think about making u equal to 1 plus x squared, so du would be 2x dx, so dividing by 2 maybe takes this out. Okay, and then do the integral that way. So again, pause here, or solve those. For 1 and 2, you'll just be answering C or D, converge or diverge, and for number 3, of course, you'll be giving the answer to that question from an old AP exam. So we're going to talk about ratio test. Now, the ratio test is one of my favorites because, to me, it is really kind of an intuitive test. It makes really, really good sense. The idea is if I were to take the sequence that defines the series, for example, 1 over n factorial here, if I were to evaluate the next term in the sequence and divide it by the nth term, so if I take a term and divide it by the term previous to it, and I get an answer less than 1, and of course that would mean that the n plus first term, the numerator here, is smaller than the nth term. That means that the series converges. And think about that. Doesn't that make sense? If we can prove that the terms continuously get smaller, that the series would converge. Likewise, it will diverge if that ratio is greater than 1. Now you'll notice there is nothing here about it being equal to 1. If the ratio came out to be equal to 1, we'd have to use a different test. Okay, so let's do one here. The n plus first term would be 1 over n plus 1 factorial. Then we divide it by the nth term, which is just 1 over n factorial. So you notice I just replaced the n with an n plus 1 to get the next term. And then we're going to take the limit as n approaches infinity. Well, of course, dividing by a fraction, I'm just going to zip this over and multiply by the reciprocal. Okay, cross this out. Well, n factorial divided by n plus 1 factorial, if I could just maybe make a little note here, that n factorial is n times n minus 1 times n minus 2 times n minus 3, and so on. And of course, n plus 1 factorial is n plus 1 multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3, and so on. So what you're going to see here is a mass of cancellations. And all we're going to be left with is 1 over n plus 1. And remember, we're taking the limit as n goes to infinity, and of course that is 0. 0 being less than 1 means that this series, I'm going to put a big C, converges. Okay, that's the ratio test. Let's do another one. So in this example, we've got n over 2 to the n. Now, one of the things that's, or a couple of instances where it's really nice to use ratio test are exponents and factorials. Okay, so this is a great opportunity to use it because it's 2 to the n. So let me do this. The next term would be n plus 1 over 2 to the n plus 1, divided by the current term, n over 2 to the n. We take the limit as n approaches infinity. Okay, well again, you know, I like to multiply here by the reciprocal. That. Well, 2 to the n divided by 2 to the n plus 1, this cancels with all but one of the 2's in the denominator. Okay, so what we have left on top is n plus 1, and what we have left in the denominator is 2n, and the limit as n approaches infinity, same power on top and bottom, so it's 1/2. Well, 1/2 is less than 1, so this converges. Okay, but less than 1. Now again, let me just go back through the math here. You know, we could rewrite, maybe I could even do this. Let me just kind of zip this right down here. Remember, 2 to the n plus 1 can be written as 2 multiplied by 2 to the n. And then you can see how that 2 to the n on the top cancels with the 2 to the n on the bottom, and you're just left with a 2. Okay? Some great algebra skills here are needed to really do a nice job with the ratio test. All right, the next one, e to the n over n to the 50th. Again, a great opportunity to use ratio test because we've got exponents. Okay, so e to the n plus 1 over n plus 1 to the 50th, divided by the current term, e to the n over n to the 50th. Okay, let me bring this up. So n to the 50th over e to the n, cross that out. So again, e to the n plus 1 over e to the n, well, all of these e's, or all except one of the e's cancels with all the e's on the bottom. So what we have left is e multiplied by n to the 50th over n plus 1 to the 50th. We're doing the limit as n approaches infinity. So I want you to just think about this right here, the denominator, okay? Because we could actually go through this and try and do this with L'Hopital's rule, but I think we can reason our way through this. If the bottom were n plus 1, let's just say squared, we could expand it and get n squared plus 2n plus 1. If it were n plus 1 cubed, we'd have n cubed plus 3n squared plus 3n plus 1. If it were n plus 1 to the 4th, be n to the 4th plus 4n cubed plus, and so on. So n plus 1 to the 50th, if I actually expanded it out, I'd have n to the 50th plus 50 n to the 49th, and then it would just go on from there. I'd have all those terms, but the highest power would be 50. So we've got the same power on top and bottom. So we use the coefficients. Well, the coefficient on the top is e, coefficient on the bottom is 1, so it's e. The limit is e, and e is greater than 1, so this diverges. Okay, so it's a really slick test. We've just got to prove that that ratio comes out to be less than 1. We get a convergence series, greater than 1, divergence series. Let's do one more. So here, let's start off with our next term. So we've got n plus 1 raised to the n plus 1 over n plus 1 factorial divided by n to the n over n factorial. Limit as n approaches infinity. Bring this up. Well, this will cancel with everything factorial there, so it'll just be n plus 1. Now, what I want you to kind of see here is that n plus 1 to the n plus 1 divided by n plus 1. You see this n plus 1 left over. Well, this n plus 1 in the denominator will cancel with one of the n plus 1's in the numerator. So now, all I have left is n plus 1 to the n on top and n to the n on the bottom, which I could then rewrite like that. Now, I think you can probably maybe even reason here a little bit and say, geez, I think that's going to be greater than 1, because what I'm going to have here is something in the parentheses that's just slightly over 1 raised to infinity. So that's going to be bigger than 1. And I think then you could say greater than 1. I'm just going to kind of put this in like dashed, like, oh, it's greater than 1, and therefore we get a divergent series because it's greater than 1. But that seems really weird to be able to do, and in fact it's nice to be able to actually get the limit. Now, you could certainly set this up like we did before with L'Hopital's rule, because this is 1 to the infinity. That's one of those indeterminate forms we can use L'Hopital for. So remember, we'd say, well, y is equal to n plus 1 over n to the n. Take the natural log of both sides. Natural log of y equals n multiplied by the natural log of n plus 1 over n. Rewrite this as 1 over n. And you could now do this with L'Hopital's rule. You know, take the limit as n goes to infinity, like this, in this format. And what you would get if you did it was you would get 1. Okay? And then you'd need to remember at the very end that, oh, you know what, I used natural log, so I've got to undo that by using e. And that is the limit here. The limit is e. Now, the other way you could do this, if I could just kind of zip over here to my blank space, is you could rewrite this as n divided by n, which is 1, and 1 divided by n raised to the n. And this is that definition of e that we talked about, you know, dealing with continuous growth. So maybe you could have caught it that way as well. So either way, it's, you know, there are a lot of different ways to see that this one diverges. As I said, you could probably just reason to it right here. You could say this is over 1 and it's raised to infinity, so this is greater than 1. But it's certainly much nicer to actually be able to get the limit, you know, using L'Hopital's rule. So a very nice test. Again, the ratio test, remember, it's next term divided by the current term. Do the limit as n goes to infinity. If you get an answer less than a limit less than 1, it converges. The series converges. Greater than 1, the series diverges.